Swayam Prabha. Digital India. Educated India.
Right? And then I'm going to have for these two also, this is S6, S4, I'm yet to draw S4. So from here it will start and it will go through this. This is going to be S4. Right? So when I am having the voltages, the pulses, so this is pulses to A phase devices, and this is pulses to B phase devices, and this is pulses to C phase. Right? So if I try to look at actually what is the value of the voltage during this particular time. With respect to neutral, I have to see what is the voltage across each of the loads. Right? That is what will give me exactly whatever is the phase voltage of the load. We are looking at the phase voltage of the load. So if I am looking at the phase voltage of the load, when S1 is conducting, I am going to have S1 and S6 are conducting, I am going to have VAB is equal to VDC when 1 and 6 are conducting. Right? So I am going to have VAN equal to VDC by 2, VBN equal to minus VDC by 2. Because I am assuming that it is all balanced load, completely balanced load. That's how it is going to be. So I should be able to say that whatever are the pulses I have got, exactly they are the magnitude of voltages also across the load phase, but only thing is it is each of it is VDC by 2, not VDC itself. It is going to be VDC by 2. So I'm going to have VDC by 2. This is also going to be equal to VDC by 2, each of them. Right? So whatever I have got, I should be able to directly draw them as the phase voltages. Right? How will you get now line to line voltages? That's what you have to check. So we have said VAB equal to VDC, agreed, but we can also get what is the line to line voltages by subtracting VAN minus whatever is my VBN directly. So if I have actually, if I want in this particular case, this is VDC by 2 minus VDC by 2. So it is VDC minus VDC by 2. So this is VDC. So let me write VAB, or shall we draw it here itself so that the time scale is exactly the same. So VAB is going to be VDC during this portion. Right? What is going to be the next value of voltage? Here I am having 0 volts as VB, whereas here it is going to be VDC by 2. So I will have during this portion, I will have VDC by 2 as the voltage. So this is VDC, whereas this is VDC by 2. Please note that this is going to be my line to line voltage. Right? After that, I am going to have S3, which is actually VDC by 2. So this is VDC by 2. So I am going to have minus VDC by 2 here for another 60-degree duration. So this is going to be minus VDC by 2. After that, I am going to have this and 4, both of them conducting. So I am going to have minus VDC by 2 minus VDC by 2. So that will be minus VDC. So I am going to have a voltage like this, which is actually VDC. Then this is going to be just minus VDC by 2 itself. So essentially my waveform will be somewhat like this. I am having first VDC, then VDC by 2, then minus VDC by 2, then VDC, then again this, and so on. This is going to repeat itself. So each of them is VDC and VDC by 2. Please note, what we applied was just VDC, but we are essentially getting 2 levels of voltage on the positive side and 2 levels of voltage in the negative side as well, as far as the line-to-line voltage is concerned. If I look at the line-to-line voltage, it is going to oscillate between VDC by 2 and VDC every time in the positive side as well as negative side. So similarly, you should be able to draw what is VBC and VCA and so on. All of them will be displaced from each other by 120 degrees at the fundamental frequency, whatever is my frequency that I have chosen to turn on and turn off. Right? Now this is for 120 degree conduction mode. What we analyzed now was 120 degree conduction mode. So in 120 degree conduction mode, what I look at is the load phase voltage that will be having either VDC level, VDC by 2 level or 0 level. We don't have anything in between. Whereas the line-to-line voltages are going to have 3 levels basically. And there is no 0 voltage interval at all in any of the load voltages in the line-to-line. So if I look at the 180 degree conduction mode, so let us again take the same inverter. Yeah. Three stages are because if I am not having any voltage at all in B, so whatever is my A phase voltage, that is returning through the third phase, not through B. It is returning through C phase. So B phase is not at all involved. There is no current through B phase. So B phase is dead. So if I want to look at what is VAB, I have to essentially subtract VBN from VAN. VBN is 0. So VAN, whatever is the value which is VDC by 2, that is coming up. Right? Yeah, but minus VDC by 2 is also there. Yeah, 1, 2, 3, 4. You will not have any 0 at all in this case. There is no 0. That's what I said. There is nothing like a dead band, a complete 0. That is not existing in the line-to-line voltage in 120 degree conduction mode. Right? And we are analyzing it with respect to R load. Because if we involve RL load, the complications would multiply. Because the diodes will get into conduction and it is very difficult to say, you know, how long the diode is going to conduct. So you may have the 3 phases involvement. All those things will get into picture. So it's not easy to analyze an inverter with RL load, especially in 3 phase, especially in 120 degree conduction mode, because they're assuming that that phase should stop right there, and it is not going to stop. We know. That's the reason. Right? So in 180 degree conduction mode, this is S1, this is S4, S3, S6, S5 and S2. And we are going to have A phase, B phase and C phase star connected. Again, I am taking star connected loads. Okay? Delta and star normally would be a dual of each other. So please draw the waveform corresponding to delta a little later for 120 as well as 180. You would see that the phase voltages and line voltages reverse their roles. Actually in terms of the shape, what you get. So let us try to take a look at 180 degree conduction mode. So this is ZC, this is ZB and this is ZA and this is the neutral. And this is VDC. Right? If each device has to conduct for 180 degrees, clearly I have to have 1, 2, 3 conducting for 60 degrees. 2, 3, 4 conducting for the next 60 degrees. 3, 4, 5 and so on and so forth. So So every device will conduct for 60 plus 60 plus 60, 180 degrees. So you will have 3 devices overlapping together, right? So I'm going to have 1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 6, 5, 6, 1, 6, 1, 2. These are going to be the combinations that I will have. So whenever I'm going to have, let us say, for example, 1, 2 and 3. You have to imagine something similar to what we did in commutation overlap. So 1 and 3 both are on the positive side, whereas 2 is on the negative side. So I will have it as though this is my VDC, what I am applying, and this is 1 and this is 3. Right? So let us say this is 1 and this is 3. And through 1, I am going to connect ZA. And through 3, I am going to connect ZB. Now these two are together, and from here, I am going to have ZC, which is connected to the negative through 2. Right? This is the equivalent circuit that I am going to have for the inverter. During 1, 2 and 3 conducting, this is how it is going to be. Please note that these two are in parallel. So obviously whatever is the current that I am going to get, that has to be divided into 2 halves. So the voltage drop that happens here will be half of the voltage drop of this. Together they have to make up for VDC. So obviously this will be 2 by 3 VDC, that will be 1 by 3 VDC. Right? So I'm going to have the voltage drop here to be 2 by 3 VDC, whereas the voltage drop here to be VDC by 3. And this is my neutral. You get my point? That's how you are going to have the voltage drop. So if I try to draw what is the voltage waveform corresponding to this particular interval, right? So let me probably again divide this into 2 180 degree interval and 60, 60 and so on, right? So I'm going to have actually, let me try to draw what is VAN. So VAN during this particular duration is going to be plus VDC by 3. So it is going to be plus VDC by 3. Right? After this I am going to have 2, 3, 4. And please note 4 is also corresponding to A phase. And 2 and 4 both of them are conducting parallelly. So they will have minus VDC by 3 across each of them. So 2 corresponds to C phase, 4 corresponds to A phase, and it will be minus VDC by 3. So I should have from here, it will jump to minus VDC by 3. This is 4 conducting, and here it is going to be 1, 2, 3 conducting. So along with 4, it is 2 and 3. They are conducting. Now when 2, 3, 4, the next one is 3, 4, 5. And 4 is the only negative side device conducting. So that will be minus 2 by 3 VDC. So I will have minus 2 by 3 VDC coming up. So this is minus 2 by 3 VDC. This will be 3, 4, 5. Right? So like this we should be able to definitely infer 4, 5, 6 and so on and so forth. So this is going to be 4, 5, 6. Then I'm going to have 5, 6, 1. Then 6, 1, 2. And then 1, 2, 3 again. Right? So you can see again that phase voltage in this particular case has basically plus VDC, plus 2 by 3 VDC, then minus 2 by 3 VDC, plus VDC by 3 and minus VDC by 3. So you have basically 4 different levels that are coming up in this phase voltage as compared to what we got in the other 120 degree conduction. Right? So we should be able to draw similarly. So if this is the way it is as far as A phase is, VA is concerned, VB should be essentially 120 degree shifted. So this is 120, so I should have something like this, I suppose. Something like this, I suppose. Right? And then this should be somewhat like this. So this is VB, VBN. This is VBN. 120 degree shifted beyond whatever is your VAN. So I have just taken this point and I have shifted it by 120 degrees. That's all. That's what I have done. Right? I'm sure when you analyze, you will get it this way. It should come this way. Otherwise, we have done something wrong with the analysis. So how will you get now line to line voltage? Let's say this is VBN. So if I want VAB, let's try to get VAB. So this is A and this is B. This is also VDC by 3 and this is also plus VDC by 3. So during this duration, I'm going to have essentially 0 voltage. Right? We have 0 voltage. After that, I have minus 2 by 3 VDC and this is plus 2 by 3 VDC. So 2 by 3 minus 2 by 3 minus 2 by 3 minus 4 by 3 VDC we'll get. Isn't it? I hope this will be minus VDC because this is minus VDC by 3 minus 2 by 3 VDC. This is VDC itself. This is VDC itself. After this, this is 2 by 3 VDC minus 2 by 3 VDC and this is VDC by 3. Yeah, so this is again minus VDC itself. So I will have one more minus VDC. This interval will also be minus VDC. Then I will have here this value and these value are coinciding with each other. So I will have 0 voltage. I hope so that this will be something like this, plus VDC and plus VDC. Just by, half-wave symmetry, I'm drawing it. That's all. Please note that compared to the previous case, this has exactly been opposite. Like there, the line-to-line voltage, what we got was the three-stepped or six-stepped waveform, whereas this was, a square wave. The phase voltage was a square wave. Here it is exactly vice versa. That's all is the difference. When you analyze delta, you have to be a little careful. There is no neutral. So what you are getting as the voltage across each of the phase loads will also be line voltage. So that will be in all probability equal to VDC itself. So you have to be a little careful. You get my point. I'm trying to say that if this load, whatever is connected is in delta, right? This is 1, this is 2, and this is 3. Each of them is going to be connected to the terminals, that is the mesh point. So we are going to have, let us say this is A, this is B, and this is C. So this will be VAB with the voltage rising in this direction, right? And so on and so forth. That's how it is going to be. So this point as well as this point, for example, will be connected to the DC link if I am having, say, one of these switches and one of these switches conduct. So I will have essentially VDC directly coming across any of the phase loads. So the phase voltages will come out to be VDC every time when the appropriate switches are on. So please make sure that you take the switches correctly, and ABC you number in this way, like name in this way, and then make sure that you draw VAB, VBC and VCA. What you are drawing is line to line. The line to line voltages, which are happening to be the phase voltages as well, because it is delta. Right? So please draw that and check it out whether you are able to, and for 120 degree as well as 180 degree conduction mode. Please try to draw those and then see what can be, the output voltage. Right? Now so far whatever we have seen, whether it is three phase or single phase, all of them essentially are having the output as a function of VDC. Right? Either VDC by 3 or 2 VDC by 3 or whatever. And we don't have any control over the magnitude of any of these voltages, because we are keeping the switch on for entire 120 degree or entire 180 degree, whatever be the case. So if I am having a fixed value of DC voltage, I will also have a fixed value of output voltage. Only the frequency I will have control. I will not have any control over the magnitude of output voltage. That is one problem. Second problem is, all the waveforms that we have got, all these things are far from being sinusoidal. They are not sinusoidal. And if I have to adjust, a motor drive to a particular frequency, and then I want it to run very exactly at that particular speed without any torque pulsations and so on and so forth, I definitely need to make sure that the voltages are somewhat close to sinusoid. I may not be able to get exact sinusoid, but I may be able to get it close to a sinusoid by eliminating at least some harmonics. So for these two purposes, that is, one is to adjust the magnitude of output voltage, because input is also fixed. I am having a stiff voltage source, which means my input is fixed. With fixed value of input voltage, I want to have a variable value of output voltage. So we are essentially looking at, first of all, magnitude being controlled. The second one is to eliminate harmonics, rather to make the fundamental dominate the output. These are the major purposes of PWM control. So pulse width modulation control is generally employed in voltage source inverters to fulfill these two requirements basically, which are mainly meant for motor drives, because motor drives are the ones which are probably going to require variable value of voltage and variable value of frequency, as well as elimination of harmonics. So in this case, first of all, the simplest thing to modify the magnitude will be, rather than having the complete 180 degree, what we had as the voltage, let me try to have it only for, let us say, part of the duration. And I would like to symmetrically place it. What I mean is, if I call this angle as alpha, I would like this angle also to be alpha. And here is my 180 degrees. So this will be 180 plus alpha, and this will be 360 minus alpha. So I should try to place the pulse in such a way that it is symmetrically placed whenever I look at any half cycle as such. And the other half cycle is exactly symmetrical as compared to the previous one. This will ensure that I am not going to have, first of all, DC component, and also My fundamental will not be shifted with respect to the original square wave I have taken. So if I try to draw the fundamental corresponding to this, maybe I will have it somewhat like this, much less in terms of magnitude, agreed. But it will not be displaced from the original zero crossing of my square wave. So this is known as single pulse width modulation. We have only one single pulse corresponding to positive half cycle, one single pulse corresponding to negative half cycle, and they are essentially, adjusted. Both these pulses are adjusted. So this is essentially single pulse width modulation. This will not have much of impact on the harmonic content. I may not be able to eliminate the harmonics because I'm not really making the pulse width vary as per the sinusoidal magnitude. I'm having only one pulse, and that maximum pulse is near the 90-degree point, and it is spread out completely. So this will not allow me to eliminate the harmonics much. I may be able to get multiple pulse width modulation, but I'm going to have, in this case, the first one I'm discussing is equal width. I'm not really modulating the width of this pulse as per the magnitude of the or amplitude of the sine wave at that point in time. So I may be able to get, say, one pulse, then second pulse, then third pulse, fourth pulse. Similarly, I may have one pulse, second pulse, third pulse, and fourth pulse. All of them are of equal width. It doesn't serve any other purpose again other than adjusting the magnitude. I may turn it on and turn it off several times. So I have maybe multiple number of angles that I can adjust so that I will be able to adjust the magnitude of the output. So I may call this as alpha 1, alpha 2, alpha 3, alpha 4. Then I can say this is 180 minus alpha 4, 180 minus alpha 3, 180 minus alpha 2, 180 minus alpha 1. On the other side it will be 180 plus alpha 1, 180 plus alpha 2, and so on. So I can make them essentially symmetrical. That is possible. So this will give me probably multiple variables to be adjusted so that I arrive at a particular magnitude. That's it. Nothing more than that. So this is also not good for eliminating the harmonics. But rather than that, the final one what we will be concentrating upon is sinusoidal pulse width modulation technique. Right? So this is essentially derived from by having a sinusoidal wave which I want to arrive at, and I'm going to compare that with a very high frequency triangular wave. I have shown it here as though it is only having a frequency of 1, 2, 3, 4, about 5 times, not even 5 times, less than that, 4.5 times or something. So if I have a larger frequency triangular wave compared with that of a sine wave, I compare the two. Wherever the sine wave is having a higher magnitude, I will have a positive pulse. Wherever the sine wave is having a lower magnitude than the triangular wave, I'll have a negative pulse. So I'm going to essentially fire the positive devices S1 and S4 during the positive pulse and S2 and S3 during the negative pulse. So this is essentially the basic operation of a sinusoidal PWM. So we will look at sinusoidal PWM in the next class.